PPT which I made. Here for this PPT, the project which we had been given, like we were 200 odd students there, and this was the height of COVID. So like we couldn't have some like actual data from any company. So what was suggested to us was to take some dummy data, and based on that, this is a mock project which we had made for the yellow belt. So the project was improving PET production. DuPont Limited was just a dummy company given to us. So yeah, go on. Himanshu, you're saying something? Himanshu, we can't hear you. Could you type it in the chat box?
Hello.
Himanshu, should we proceed, or like you wanted to talk about something? Okay, so let's move ahead. So coming first to the define phase, like you said you're familiar with DMAIC. So DMAIC starts with define phase. Here in the define phase, we try to define the process and the problem which is there. And the first thing which we do here is that we try to identify the process CTQ. Now, CTQ is critical to quality. What is the thing that is the most important for this project? What is the thing that will make or break the project? So for this case, the project was improving PET production, and so the critical to quality factor was production rate should at least be 750 tons per day. And now, but how will we get the CTQ? So we get the CTQ by the voice of customer. And the voice of customer is the company management, because company management are the people who are going to get benefited if the production is increased. The production increase, the finance of the company will get better. So it's the company management who is the customer. And the voice of the customer, like someone from the company may have said, currently like we are not getting the 750 tons per day of production which is required by our customer, and so we are not able to fulfill our the orders which has been requested from us, and so we need 750 tons per day should be ready on schedule. That's the voice of the customer, and based on that the CTQ was defined. So this is the start of the define phase actually when we talk about the actual Six Sigma project. Going ahead. So now, for those who may not be aware, like here I have a small representation of the PET production process. So for the PET production process, we have two raw materials, which are ethylene glycol and terephthalic acid. So ethylene glycol is also called as monoethylene glycol (MEG), and terephthalic acid is also called as PTA because like it is referred to as purified terephthalic acid in the industry. So one thing I would like to ask you is, like in this earlier slide, when we are talking about CTQ, why are we focusing so much on customers? Can someone tell me about this? Any volunteers? Why is the customer considered to be so important in the Six Sigma process?
So because we need to produce according to their needs, means according to we need to yield the product according to the need of the customers.
Rightly said. So basically, like there are two philosophies of production. One is called a push system and one is called a pull system. In push system, you first make the product and then you try to sell it to the customer. While in the pull system, you try to make the product like exactly according to consumer requirements. So that's the pull system. And in Six Sigma, we try to like implement a pull system of production. And so that's why the customer requirements are very much important to us. And so like customer has a very high focus in both Six Sigma and Lean actually. Moving ahead. So coming to the SIPOC, this is a tool which stands for suppliers, inputs, process, outputs, and customers. It provides a high-level view of the process. So sometimes like people also use COPIS, COPIS, like because customer is the main focus. Some people like to start like this table from they start from customers. It's the entirely opposite, like, but it's basically the same thing. So now talking about the project considered here of PET production, some dummy suppliers were considered here. The inputs, as I told you earlier, the MEG and PT are the raw materials, utilities, catalyst, manpower, equipment, some of the inputs. The process is considered here. Then the output is the PET resin, and the consumer, as highlighted earlier, is the company management. Here, basically, during this entire project, at least in our case, because it was the height of COVID and we didn't have any actual data from the industry, the main focus was only on the application of Six Sigma tools and not on the chemical engineering aspects. So till here, while a little bit of like we have thought about like what are the top manufacturers of MEG or PT, and that's why some names of companies like Reliance or Adani have been put. Going ahead, you will see that a lot of it is dummy data. So coming to the project charter. So when we come in the define phase, project chart is one of the most important parts of the project, because like the entire thing what we are going to project depends on the project charter. Like we talk about what is the problem statement, what is the scope. So now scope, you would say like, why is it that important? So the importance of scope arises because based on the current scope, like you will talk about the timeline of the project. If sometime later the scope increases, there's some addition in the scope, something else needs to be considered too, then the scope of the project will get increased and the timeline will get impacted. So that's why at the start itself we try to put all of the things in, and so project chart is considered as one of the most important documents in the define phase. So now in this project charter here, a resource plan and team members, here some dummy data has been put. The problem statement we have considered was the average PET production is 745 tons per day, but the plant rated capacity was 8,000 tons per day. Now, directly you're not able to achieve 800, so at least like the goal statement was improve PET production to minimum of 750 tons per day by November 2020. So as I said, this is like this is a PPT from 2 years back. The consumer CTQ was told earlier, and for the financial opportunities, again some dummy data was considered. Now this was a high-level improvement plan timeline. Basically, this is based on the milestones, the time which was present earlier. This was again some dummy data. Now coming to the measure phase. In the measure phase, we try to analyze the we try to measure the current performance. And to measure the current performance, the most important thing you need is a data collection plan. Data can't be collected randomly, and because data is considered to be very important in a Six Sigma project, because like in Six Sigma, what we try to do is all the decisions we try to take care of it on a quantitative basis and not a qualitative basis. So that's the entire goal of Six Sigma here. Like data should be the key to everything. So for talking about the data collection worksheet, like the CTQ is PET production rate. How it can be measured? So it can be measured by tons of PET produced per day. Data type is continuous. For this, how much sampling we should be considered? So again, here some data, dummy data was considered that like from the past 30 days of operation, data can be considered. And this data is to be collected from the PET logbook, where actually the data is coming via flow meter. And this data is to be measured by the plant operators. So now, like this PET production data was assumed here. Some of the people who did the Six Sigma projects after me, after the COVID pandemic was not so not so problematic. In their case, they have used real data, but this year we had used assumed data here. So for each of the dates, I had assumed some data. The data, as you can see, is that in most of the days, the production is below 750 tons per day, and our goal is to make it above 750 tons per day. That's the project which was undertaken. So now in the measure phase, we try to calculate the current sigma of the process. Now to calculate the current sigma of the process, a concept which you need to know is the defects per million opportunities. Are you guys aware about the concept of defects per million opportunities? Could someone volunteer for the audience to answer me?
No, sir.
Okay, I'll go into it then. So, concept of defects per million opportunities. Now you consider example of chocolates. Now see, there are four critical to quality things which are required in chocolate. There's sugar content, the melting point, the color, and the size of the chocolate. So there are four possibilities of things going wrong in a chocolate. That is what we have assumed here. The sugar content can go wrong, the melting point can go wrong, the color can go wrong, or the size can go wrong. Now, see, there are 5 chocolates. So the opportunities for defects would be like the opportunity for defects equals possibilities of defects per chocolate into the number of chocolates. So that will be 4 into 5, that is 20. So now, like, let's assume that this is the data of the chocolates which are there. These are like the 5 chocolates, the chocolate number 1, 2, 3, 4, 5. And for each of these, like there's 4 CTEs which are given, and whether they are right or they are wrong has been highlighted here. Now, can someone from the audience tell me like how many are the number of defects present here overall?
5 defects.
Right. And
Five.
how many chocolates are defective?
3.
Right. Very good.
3.
So basically, the number of defective chocolates was 3, but the number of defects was 5. In the concept of defects per million opportunities, we consider the number of defects and not the number of defective units. So the DPMO equals 5 by 20, which is the 5 was the number of the defects and 20 was the total number of opportunities for the defects into 10 raised to 6. 10 raised to 6 is to get per million opportunities. So the DPMO is 250,000 here. So this was the concept of DPMO.
So how was the opportunities calculated?
Could you repeat your query?
How were the opportunities calculated? Like how did you
Okay,
get
sure.
20?
Let's go back. Have you answered, like understood this 4 possibilities part?
Yes, yes.
Okay. So now, like the opportunities, the total opportunity is the number of defects per chocolate into number of chocolates. Like defects per unit into number of units. That's the possibility of the defects which can occur.
Got it.
Okay, sure. Let's move ahead then. So now that you have understood this, going ahead, now once the DPMO in the context of the PET production, let's look into that. So the number of units processed is 30. So basically, N is the 30 number of days which have been considered. Each of the day has been considered as 1 unit. So as you can see here, unit is mentioned as 1 unit is production in 1 day. So number of units processed is 30. The total number of defects made is written as 16. This was because in the data which was assumed earlier, there are 16 days where the production is below 750. So the number of defects is 16. The number of defect opportunities per unit is 1 because the only possibility of a defect here is production not reaching 750 tons per day. That's the only possibility for a defect. So the O is 1. And based on this, like as I told you earlier, based on this, DPMO can be calculated out to be like 5,33,000. And now once you get the DPMO, you can use various tables which are available, like how we have like T tables, Z tables. Similarly, we have Six Sigma tables available. Or you can use some software to get the level of Six Sigma once you have the DPMO. So basically here, this actually, when I did my Six Sigma internship, we were given this Excel file where basically this Excel file is embedded in this PPT. And once you put all these numbers, the Six Sigma is calculated automatically based on the formula which has been put inside. So now, like the initial, before the project is implemented, the Six Sigma value was found out to be 1.42. And this is like the data of the daily production in a graphical format. in a format of a histogram. So as you can see, well, on some days the production is about 750 tons per day. On other days, the production is below 750. And our objective is to basically try to shift the histogram of daily PET production to the right, such that 750 tons per day and not 730 tons per day. Like currently 730 days per day is the minimum. We want like 750 should be the minimum here. That's the aim of the project. Now coming to the analyze phase. Now in case of the analyze phase, we try to analyze the process for issues and root causes. So the first thing which we did here was basically we tried we tried to find all we tried to list down all the possible causes which could occur for this which could cause this effect. Like the effect was PET production being less than 750 tons per day. On the left hand side, all the causes which we could think of, we have listed them down here. And talking about this diagram, this is called a cause or effect diagram, a fishbone diagram, or Ishikawa diagram. And it is used while brainstorming to get the root of the problem. All the possible issues, like even the rarest of the rare issue that you can think of, you have to put it down here. And this diagram looks like a fishbone, so that's why it's called a fishbone diagram. And typically the analysis done is using the concept of 5M and 1E. This acronym is for management, machine, manpower. Manpower is called personnel here in this case. Method, material, and environment, like 5M and 1E. And for various types of industry, different acronyms can be used. So like all the causes were listed down here. This causes, we try to prioritize it. So basically, this is a qualitative analysis currently. We try to prioritize all the causes based on whether they are in our control or out of our control and their impact. And once this have been classified like has been done here, first priority it is given to in our control and high impact causes. Like this causes present here. This is because like they are in our control and like they have an high impact and which will like directly affect the production which is there. Talking about examples of in our control and out of our control. In our control, like it can be studying more for the exams to get more marks, and out of our control is something like the COVID crisis, which a black swan event over which no one has any control. This is just a qualitative analysis, and like this is just some dummy data present here. And this was just done to show showcase the implementation of this prioritization matrix. Now coming to the Pareto analysis. Pareto is a statistical tool in decision making for the selection of limited number of tasks that can produce significant overall effect. It is also known as 80-20 rule. Like the Pareto principle states that 20% of the work you do generates 80% of the benefit. And this is depicted by the slogan vital few and travel many. So again for this, like all the causes were listed down, and for each of these causes some frequency was assumed. And based on this, a Pareto chart was made. So here, as you can see, like leakages, cavitation due to pumps, high reflux ratio, and high temperature, lack of planning. Like these are some of the dummy causes which we had put here, but based on again like the dummy frequency which we had put, these were identified. These 5 were identified as the vital few causes because like they give the 80% of the cumulative cause for errors. So those have been listed down here, the 5 vital causes. Going ahead, we come to the testing of hypothesis. So now basically you have found the vital causes, but now you have to do testing hypothesis to find the root causes from this vital few causes. Basically, we try to find out whether there exists a relationship between the vital few causes and PET production, or whether it's just coincidence, like there's some relation being shown here. And for this, like before going to the testing hypothesis, like I would like to talk about the various types of data which are there. So there are 2 types of data basically. They are attributive data, which is the qualitative data, and the variable data, which is the quantitative data. Attributed data is further classified into nominal data and ordinal data. Nominal data is non-numerical and does not have a definite order. Example like Marshall status, good or bad product. In case of ordinal data, there's some non-numerical, but they have a meaningful order. Like basically a satisfaction rating or a hierarchy. Basically students, teaching assistant, assistant professor, associate professor, professor. That hierarchy, if you have data in that order, then it will be an ordinal data. And to like analyze attributed data, we use box plot in the case of hypothesis testing, and in case of variable data, like you would be knowing about this, like they are discrete data and continuous data. And for variable data, scatter plot is usually used for hypothesis testing. Basically, before heading to hypothesis testing, I just wanted to talk about why in some places a box plot has been used and why in some cases like scatter plot has been used. So coming to the testing of a hypothesis, again your data was assumed for each of the day, like leaking, leakage, no leakage, like some data was randomly assumed. Whether there's a problem of cavitation of pump or not, that was assumed. Some reflux ratio was assumed, some temperature was assumed, and whether the issue was due to planning or it was not due to planning. Like this is just some dummy data which has been put here to like basically the only use of this data is to have some data so that the analysis which is further can be done. So now leakage or no leakage, it's an attributive data, and so that's why a box plot was used for analysis. And so here, as you can see, like this seems to be a perceptible relationship between leakage and the production of PET. If leakage happens, the production of PET is less. Now, talking about pump cavitation and the production of PET, similarly here, you can see that like when there's cavitation, there's a perceptible drop in the PET production. And so like this is also one of the root cause. The leakage was a root cause, pump cavitation is also a root cause. But if you talk about planning, there doesn't seem to be much of a like drop in PET production, whether there's planning or there's no planning. Talking about reflux ratio, like again based on the data which was assumed, the R square value is coming as high, and so like we can say that there's a relationship between the reflux ratio and the production of PET. At a higher reflux ratio, the production of PET is lower. Talking about temperature, the R square value is very low here, so we can see that there's no relationship between temperature and the production of PET. So basically, for like all of this analysis which was done here, all the dummy data has been used, and like chemical engineering aspects have not been like clearly thought of. Like we just took some data and we had put those here. So the root causes were leakages, pump cavitation, and reflux ratio. So basically, first we identified the vital few causes based on the Pareto analysis, and now based on this hypothesis testing, we identified the root causes. Now, before going ahead, I'd just like to highlight, like as it's your yellow belt training internship which is going on, like here we just go on visual data. But when we talk about higher belts, like we don't go on visual data. So what we do is even after this further analysis is done, and based on that that analysis, we'll decide whether like it's a root cause or not a root cause. But considering the purview of yellow belt, this is enough. So now you must be curious, like what is this box plot exactly? Scatter plot, I'm quite sure that all of you must have used it one or the other times in Excel, but what is this box plot here? So I would like to highlight some things about that. So box plot is also called a box and a whisker plot, and also called a 5-number summary. So this involves 5 numbers: the minimum, first quartile, median or the second quartile, third quartile, and the maximum. So this thing in between is the box, and these 2 things on the side are the whiskers. So that's why it's also called a box and a whisker plot. A box and a whisker plot, and in this case, the median is directly like it's in the center. So that's called a box plot with no skew. We can also have box plot with negative skew or positive skew. So when the positive skew is when the Q2, the median is near Q1, and negative skew is when the median, that is Q2, is near Q3. So like so going ahead. Now what are quartiles? So quartiles mark each 25% of a set of data. The first quartile is the 25th percentile, the second quartile is the 58th percentile, and the third quartile is 75th percentile. And like this is the method to calculate the quartiles. First you set up the data from the lowest to highest. Then you find the median. The median is the second quartile. Then the part above the median, you find the median of that, and the median of the part above the median of the entire data is the lower quartile, which is Q1, and the median of the upper half of the data is upper quartile Q3. There's just some like miscellaneous knowledge about box plot. Going ahead. Now, in this analyze phase itself, FMEA is something which comes up. FMEA is failure modes and effects analysis. So now, are you familiar with FMEA?
No, sir.
Okay.
No, sir.
So let's go into that then. Just a minute. So FMEA, failure modes and effect analysis, something which like the US military came up, and it's a risk assessment tool that evaluates the severity, occurrence, and the detection of risk to prioritize like which of the problems has to be prioritized as because they are the most urgent. And this is done based on a scoring matrix for the severity, occurrence, and detection. The score of 1 indicates a low risk, and a score of 10 indicates a high risk. So like in case of the severity, like 1 is low risk, 10 is high risk, and low is better. In case of occurrence of defect, if it's a low probability of the risk happening, then it's 1. If there's a very high probability, then it's 10. And the detection of the data, here we like consider what is the probability of discovering the data before the customer discovers the error. Because like anytime discovering an error ourselves is always better rather than like our customer discovering the error and having to send all of the material back to us. So like if the failure is easy to discover, it gets a score of 1, and in case it's undetectable, it's assigned a score of 10. And based on this, we calculate a risk priority number, RN, risk priority number, which is the product of severity, occurrence, and the detection. Like as told earlier, low score for severity is better, low score for occurrence is better, and low score for detection is better. So overall, a low RNP value is better. And processes that have a high RNP value are the ones which have to be like, we should put the most focus upon it. So if an FMEA, a failure modes and effect analysis was done here. Potential failure modes, some of the highest potential failure modes which are identified in Pareto analysis. For that, this analysis was done. First, we have the potential failure mode. Then we have the potential effects of the failure to like see for ourselves, because like a Six Sigma project may involve a lot of people. Some people may be actually working in the factory. Some people may be the management who may not be aware of what happens in the factory actually. So that's why we try to make a document like this so that it's in front of the entire Six Sigma project group which is there. So like the potential failure mode, potential effects for analysis, then we assign the severity, then the potential cause for failure, occurrence, control measures, detection, and as told earlier, a risk priority number is calculated based on the product of severity, occurrence, and detection. And based on this risk priority number, the potential failure modes which have the highest risk priority numbers, they have to be given the most priority. So in our case, like because we were assuming all the data, we assumed such data such that the risk priority numbers of these three root causes would be the highest, and for each of them, like the potential solutions which could be there, which were highlighted. So now there's like we thought of a potential failure mode of a leakage. So now a control for that was maintenance, and the action that could be taken, the solution that could be taken was frequent maintenance. For pump cavitation, like a potential cause, like the maintenance control is against, like if we do maintenance, pump cavitation may not happen. And to take this, the action to be taken is frequent maintenance to ensure there's no blockage and redesign the pipeline to stop pump cavitation. Coming to high reflux ratio, again, like we could have some additional manual control to it, like it was highlighted here, and action taken could be maintain reflux ratio manually or like have some automated system to maintain it better. Now, basically, this was still the analyze phase. So here, basically, we first identified the vital few causes, then we identified the root causes, then we identified the like the potential actions could be taken for these root causes, and now coming to the improve phase. Now in this improve phase, we try to determine and implement improvement actions. So first of all, in the improve phase, what we do is the improvement context analysis. Improvement context analysis is done to find out of all the solutions present, which ones are the solutions which we should implement. So for that, like basically first we list down all the criteria which we require. The criteria requirements that you want your solution to meet. There are some criteria which are must criteria. Like for example, feasibility may be a must criteria, because of like a solution is not feasible, there's no point of implementing it, right? So any solution which does not meet even one of the must criteria has to be eliminated. So the criteria which we highlighted here were cheap solution, quick to implement, high impact on CTU, which is critical to quality, like the production rate which you want, and feasibility. For each of this, some dummy weights were assigned. Then again, for a frequent maintenance, like a score was assigned, whether based on how cheap it is to implement, how quick it is to implement, how much of an impact it will have on CTQ, how much feasible it is. Based on that, like this matrix was done. And from this matrix, it is clear that frequent maintenance is a very good solution for increasing the production, followed by better process to maintain the reflux ratio. Now, talking about redesigning the pipeline, the feasibility has been put as 1 year, because redesigning the pipeline is logically will be the last option, because production have to be stopped for some days. You'll have to invest in new capex, so that's something which you don't want to do and which is not feasible. So based on this, like we first calculated this weighted score, and based on that, like we got to this conclusions. Now going ahead, like for each of the root causes, the solutions which could be taken were mentioned here. These were similar to what was highlighted earlier during the FMEA part. Now coming to the control phase, here we try to maintain the improved process once you have improved it. So this is done by continuous monitoring. So now say like you have implemented all of the new things, you have added like you have taken care that we are doing frequent maintenance, you have added some automatic systems to take care of the reflux ratio, but now you should monitor whether these are actually giving you the benefits. For that, again, we have like a data collection plan worksheet here, which is similar to what was highlighted earlier. Now, like again, here we had assumed some data, but in the actual scenario, like the data before the product, before the project is implemented and after the project is implemented would have been compared. And then we again try to calculate a Six Sigma level after this process have been implemented. So this is similar to the process which similar to like the how I highlighted earlier. And here the Six Sigma was found out to be 3.33. This is I'll highlight again here that this is all based on some dummy data because this is a mock project which we had undertaken here. And talking about the old and new control plots, old control plot would have looked something like this. The mean of the production is 745 tons per day, while in the new case we can observe that the mean itself has shifted up like to 753, which is what you wanted. So this like the project summary had been put here, that average PET production per day, like the value which was before, the value which was after, the sigma level which was there, which was after, and the DPMO value, and like basic like again the annualized benefits realized, which is again like some dummy data which is present. So basically, this was one of the main parts which I wanted to like cover today, and like the Six Sigma project, which even you will have to do. So do you guys have any like queries about this part, or should we move ahead?
Sir, I wanted to ask what is the weight of the criteria and how are all the values that you are giving in the, means how are those calculated? I was a bit confused in that.
Okay. Are you talking about the thing in the improve phase which was there?
Yes, sir. You had, means there was a chart and there was some weight of the criteria and all those written. So I could not understand that part,
Okay,
sir.
just a minute. Are you talking about this?
Yes, sir.
So here basically, as I told you earlier, like entirely we had considered some dummy data here. So like for the criteria of cheap solution, we want the weight of 4, like say, with to implement cheap solution, because like after all, if your production is increasing, cheap solution does not matter that much, right? So that's why we had put a lower weight of 4 here. For quick to implement, like how much ever time the improvement activity is taking place, for that much time you'll have to stop your process. So we had put a high weight of 8 there. For high impact on CTK, obviously the weight would be very high, because like that's the project, right, to take care of the uh, like the production rate. So that's why impact on CTQ was given a very high rate, and again feasibility was given a very high rate, because if a process is not feasible, like it can't be considered here.
The weight means which things, which of the criteria is in more priority.
Yeah. Weightage basically. So basically,
Okay, sir.
weightage years to calculate a weighted score, and on base of this weighted score, like frequent maintenance has the highest weighted score. So frequent maintenance was highlighted as the first solution. Second solution was highlighted as maintaining like a reflux ratio. And that was second solution. Redesigning the pipeline had the lowest score, so it was highlighted as like the last option. So that's the use of weightage here. Have I solved your query?
Yes, sir. Understood. Thank you, sir.
Okay. Anyone else has any other query? Anyone? Or should we move ahead? Okay, moving ahead then. So basically, like this is something which like I myself, when I started my Six Sigma journey, I found this very interesting. Like, could someone from the audience tell me like what is accuracy and what is precision, and what's the difference between these two things? Could someone volunteer? Okay, no issues.
Sir,
So, yeah, go on.
no, sir, I was
Yeah, go
just
on, go on.
thinking precision is used to achieve accuracy. Can we say that?
Okay. It's not exact, like in context of Six Sigma, your answer is not exactly right actually. So basically, it's like uh, accuracy refers to the closeness of the measurement to the correct value, and precision is the closeness of the measurements to each other, regardless of whether they are near the correct value. So, like in the examples which have been highlighted here, the first thing is accurate and precise. Like we want the bullseye, we are getting it accurate, and it's also precise because all of the measurements are close to each other. The second one is not accurate, but it's precise because like all the measurements are close to each other. The third one is accurate. It's accurate because once you take the average of all the four of these measurements, you're going to get a value which is very close to the bullseye. So this is accurate, but it is not precise. And the fourth one is not accurate and not precise. So that's actually the difference between accuracy and precision. And I myself, like, I found it very like interesting when I started my Six Sigma journey. So that's why I thought of highlighting it here. So now, could someone tell me like which of this is the best?
Accuracy.
Of these four options, like which is the best?
Accurate and precise.
Right. So accurate and precise is the best thing. That's what we should aim for. That's the very best thing which we could have. What is the second best thing here?
Not accurate and precise.
Right.
Ac-
Yeah, you had some other answer. Yeah, you could go ahead and give your reasoning behind that.
Sir, I thought the second one must be accurate and not precise because we need the correct answer in a better priority. Why should it be not accurate and not precise?
This is the same thing which I used to think of it. But when we talk about Six Sigma, if you must remember from your lecture earlier, Six Sigma we talk about lowering the variation, right? So we should have like the measurement should be as close as possible. That's the goal in Six Sigma. And so for that reason, like not accurate and precise is considered to be like the second best thing. And the reason for this is like it's not accurate, right? And because like it's being precise but it's not accurate, there must be some systematic error in the measuring instrument. Maybe you take care of that systematic error in the measuring instrument, or maybe and systematic error in the process. Once you take care of that, you will get accurate and precise. So that's why not accurate and precise is considered to be the second best thing. They just wanted to highlight something something interesting. Now, going ahead, because we have some extra time here. I will cover some extra parts which like I had kept it. I have some extra time. So now, like DMAIC process was covered earlier, but like, do you know about the approaches like for a deployment of DMAIC? Had this been covered earlier?
So you mean the
Yes, sir,
design
covered.
analysis?
Okay, fine, good. Well, are you guys aware about the ABC analysis?
No, sir.
No, sir.
No, sir.
Okay, so ABC analysis is basically like uh, uh, is someone typing something in the chat box? I can't see the chats actually. Maybe you could unmute and speak out.
If you have
Okay,
any
okay,
doubts,
fine.
please speak up. Salil, they will speak up after the lecture. When the lecture is over, I have asked him him or her. After when a lecture is over by a mentor, then he will ask questions.
Okay, sure.
Okay.
So now talking about the ABC analysis, like basically this is talking about the manufacturing industry here. But ABC analysis is implemented like in many places. So talking about the manufacturing industry, materials are classified into three classes. Class A, which are like the 10% of the materials having 70% of the cost. Example, ball bearings, which are actually very costly. Class B, 20% of the materials having 20% of the cost. And class C, 70% of the materials having 10% of the cost. Like these are like commodity products like lubricants. So now basically like this analysis can also be used in case of HR too. Now talking about like the people in the company. At the class A, you'll have the senior management, which are like the 10% of the employees which are getting the highest 70% of the salary. The 70% of the salary is going there. Like you can ABC analysis, like having different percentages in different cases. You can use ABC analysis in various cases. Now, talking about vendor management, like this is also something like which was covered towards the end of our Six Sigma course. So I thought like maybe you would like to have a flavor of it right now itself. So now in Six Sigma, like you may do everything in your own plant, but what about your suppliers, like the vendors which you have? So to ensure that you are having the best suppliers, the best vendors, we use the concept of vendor rating, where the total vendor rating is a accumulation of a quality rating, price rating, and a delivery rating. Quality rating is found by the percent of accepted items. Price rating is found by the price ratio. Delivery rating is found by the delivery promises kept, and these are multiplied by their weightages to get the ratings. And weightage, like typically in the industry, it is considered to be for the quality 70, prices 20, and delivery is 10. Because like quality has got the highest rating, because like that's the quality management thing which you are in, right? Then that's all from my side there. So these are my contact details. Like if you have any query, like you could undoubtedly ask them now itself, but if you want, you could contact me later too. Himanshu, I've finished with my part. Like if anyone has any queries, they could like ask them now.
Salil, Himanshu here. Hello.
Yeah.
Am I audible, Salil? Salil,
Yeah, you are.
we have to suggest some. We have to suggest some project topics to them also. Like I have done acetic acid production. Salil has done some other project. Please tell your subject, Salil. Top project topics of green belt and yellow belt.
So in our case, what we did is both in actually in case of my yellow belt, all of us, we had 200 odd students, and each of us was given the same topic of I think it was acetic acid production. Like all the whole class took the same topic. In case of green and black belt training, we were told to take different groups were told to take different topics, and we had taken the topic of PET production. There were some other people who had some industry connections, and they could actually get real data from the industry. And so there was not a mock project, and there was a very like a proper project which was there. So you could go ahead and choose your own topic actually, because like Six Sigma, like currently because most of you here must be chemical engineers, we are talking about a chemical engineering topic here, but Six Sigma is actually all encompassing, like from the finance industry to healthcare industry, like it can be used in innumerable industries actually. So you could take up the increasing the production of any product, any compound or product of your choice, and you could go ahead. Himanshu, anything else?
Any doubt regarding a project, because you have also made a project also from now onwards. You have studied in yesterday lecture about main about introduction of Six Sigma. Okay. From tomorrow on, next week, your lecture is of DMAIC. So tomorrow, maybe by another week, I will share the PPT and some other projects related study material. So you have to start your project as a step by step, like a defined phase. If your defined phase is completed, so you can also make your project up to defined phase. So make a group of 3 to 4 peoples, Am I audible, Salil?
You're audible.
Make a group of for 3 to 4 papers, maximum 4, minimum 3. Okay. Okay.
Okay.
Yes, sir.
What should the topics be about? I mean, some guidelines should be
Will
there.
share with you if you yes. First of all, I'll make a one Google form in which you have to fill the form. If your choice, if you have any topic, if you are interested in any topic, please fill that form. After that, we will suggest 3 to 4 topics or a one topic. Whole the class will be do on that.